Good morning, everyone. Welcome back to the third day of InGARSS 2023. Today we have with us Dr. Armando Marino as a keynote speaker. He's Associate Professor at University of Stirling, Faculty of Natural Sciences, Stirling, UK. It's my pleasure to introduce him to the gathering. Armando Marino is a senior lecturer in Earth Observation, Biological and Environmental Sciences at the University of Stirling, UK. His research interests include radar imagery for the monitoring of environment and maritime applications such as monitoring plastic pollutants, icebergs, sea ice, and other targets at sea that are of interest of environmental protection and hazard mitigation. He has worked on various projects such as multimodal data analysis for monitoring invasive aquatic weeds in India and delivering analysis-ready and value-added data to the South American Supply Chain and Farmer Advisory Services, funded by Royal Academy of Engineering and Environmental Systems Limited, respectively. And it's my pleasure and privilege to welcome you, sir, for the keynote talk on the topic, New Trends in Polarimetric Synthetic Aperture Radar. So please.
Thank you. Thanks. Yeah. Thank you, everybody. And first things I would like to say, it's really an honor for me to be here, be giving this keynote. I love this place. It's beautiful, fantastic. The conference is very, very interesting too. So really, for me, it's an honor to be able to participate to this conference with a keynote speech. And I guess next slide is this one. Let's correct that. Not this. All right. So, what we are going to talk today. Today, let's just find my position. Let's move it here. This one is the perfect. And then let's put this away. Here we go. What we are going to talk today. Today we are going to talk about this new trend or framework in polarimetric SAR. I heard that there is a big interest also in India regarding polarimetric SAR, and indeed this is a very powerful method. There are very powerful methodology that we can harness for the future of the new satellites that are coming, and there will be more and more satellites that will have this capability. So I think this is now the time to start seeing a little bit at the future. You have seen the past. And some of you may have attended the polarimetry course from Carlos 2 days ago. So you've seen what has done so far. What I want to do today is to have a look a little bit at the future, what we can expect happening or what seems to be interesting at the moment. And so this is a picture of my campus in Stirling, so in Scotland. And they're all invited to come visiting us. It's a beautiful campus, beautiful corner of the world. Also, if you have never visited Scotland, I really invite you to come and have a look at Scotland. But as you can also see, as you can hear, I'm not Scottish, I'm Italian, but I work there, and for an Italian, say that a place is good means that it's quite good. You know, we are picky with these things. So. Today, yes, I would like to talk to you about these new trends. And with new, I mean last 2-3 years. So this is mean that I have to be quite selective. Really, I'm selecting the latest trend, and I'm ignoring what is before. And there is a disclaimer that I have to do before I start, but let's go to that later. Before we start, so as an introduction, say, of what I will tell you later, I would like to talk a little bit about what is the situation of the community in the last 2-3 years, so say. And for me, the review time for me is 2 years. Every 2 years for me is a new session of polarimetry, because I align this with the PolSAR conference workshop that we have in Europe every year. For me, that is a cycle. And then you have 2-year cycle when we come back and we review what we have done so far. And if you are interested in polarimetry and you want to learn more about that, I really urge you, or will suggest you to go to this workshop, or there is also a training course before this workshop. and is really, really interesting, really focused on polarimetric SAR. If this is what you like, it's for you to go. So let's review first the 2 years before the current session. So 2019 to 20. The way I did it is by looking at the main journals where you expect to see things about polarimetry and also methodology, especially new algorithms, new methodologies, and review these journals and see a little bit how many papers we have that talk about polarimetry. In other words, they have the word polarimetry either in the title or in the abstract. And they do use polarimetric data somehow. So the 3 journals that I normally review for this are the TGRS, JSTARS, and MDPI remote sensing. This doesn't mean that these are the only journal where people in remote sensing publish. There is many more, as you know, many other wonderful, very good journals, but I think these 3 are where normally people get their new polarimetric algorithm or developments. If you develop something new, and it's not just a new application, then you generally go to TGRS or JSTAR remote sensing. This is where you normally find it. That's why I have only these 3. But there is more, as you know, there is many other journals that are very good as well. So TGRS had 72 papers talking about or with something related to polarimetry, where people were using polarimetric data. And of these, 24 was about change detection. This is possibly witness of the Sentinel-1 era, that you had this long time series. A lot of people were interested in looking at changes. But also you have other things, in related to detection, retrieval, classification, decomposition. There were 8 papers on decompositions, for instance. JSTARS, 15 papers, classification, decomposition. Decomposition still was a big thing. Remote sensing, 84 papers, so one with most paper, 26 on classification, and also talking about retrieval and detection. If we go to the most current session, say, so June 21, June 23. So I'm missing, this is not very current, I'm missing four months from now, but yeah, it's the one that I did so far. So you have to wait another 1.5 years before seeing the next from me. So again, TGRS, JSTAR, remote sensing, 89 papers from TGRS, a bit more than before. 38 JSTAR, a bit more than before. 97, a bit more than before from remote sensing. What are the topics? 21 of TGRS are about machine learning, so more than what we had before. And only 5 on decompositions, less than what we saw before. JSTARS, mostly they talk about machine learning. Only 1 paper in these 2 years was dedicated to a decomposition. Remote sensing, mostly about retrieval, and only 4 were dedicated to decompositions. So just looking at these things very quickly, say very shallowly, we can draw some conclusions, say. So it seems that the community is growing, so there is more paper. It could also be that the journal accepts more paper, which I will probably doubt, or the community is getting bigger. This is not a boom change, it's not a doubled, it's I'll say maybe 10–20% more, but still we are growing as a community. And also there is a different attitude for what I see with dual pole data. Before, dual pole was, the people were not really exploiting dual pole fully as they are doing now, so with Sentinel-1, for instance. So there is a different attitude to these 2 channels as bringing extra information, more than just having independent channels as was the attitude before. The second thing is about the composition. It seems that this is going down, and there are less and less paper dedicated to decomposition. I think this is witness to the fact that we explored most of what could be reached by these full-purpose, all-purpose decompositions. With decomposition, I mean the all-purpose one, the one that they tell you you can fit to any target, no matter what you're talking about, you can just fit it there and get your components out. And this kind of algorithms are going down, I think, because maybe we explored all is there, and now we are trying to aim at different things, more machine learning, for instance. So yeah, that is quite an interesting thing. Regarding the PolSAR community, then there is an interesting change recently, which is that we are translating the PolSAR Pro software into Python and also to be included in MAP. So some of you may be familiar with PolSAR Pro. How many people know PolSAR Pro if they've ever used? 1, 2, 3, 4, 5, 6, 7, all right. Yeah, they're looking at you and know all of you. Yes, so it's not very used, but it's a great tool. So this is a software tool, like, so you don't have to code, you just have to click buttons. And there's a lot of polarimetric algorithms, decompositions, processing. So if you are new to polarimetry, you want to try out this some processing with polarimetric data, then my suggestion is that you try first with PolSAR Pro and start having a feel of what comes out. But when you start wanting to use this more operationally or developing a bit more, say, algorithms, for instance, then PolSAR Pro is probably not the easiest because it's just this fixed tool, and you may want to have it in Python where you can change the code, you can modify everything there. This is what we are doing now. We are converting it into Python. This should be available possibly in 1 year. Some of this functionality will be available in Python, open source. Of course, everybody can use them in a GitHub, everything all available. And also will be included in this platform, which is an online platform which will contain data and processing algorithms all inside the same platform. So it's a little bit like the Google Colab that we have seen 2 days ago, but this is managed by ESA and NASA. It's an independent thing, and all the ESA, not all, most of ESA and NASA data will be inside this platform. Easy to access and with routines there too. So it will be really, I think it will really boost the utilization of this kind of data. And in general, if you want to know more about these things, just ask questions later. I'm very happy. I'm here to, I'm happy to ask questions. It makes me feel more worthwhile doing these things. So please ask questions later. Now let's start with a quick recap on polarimetry. This has to be super quick because we have spent a full day, 3 days ago, talking about that. I think you have polarimetry until your head, so I don't want to bother you too much, but just to see what we are talking about. I'll do like that, actually. So talking about polarimetry, I think most of you have experienced polarimetry, although you never used polarimetric data. So a raise of hands, how many of you, do you think you have ever experienced polarimetry? Raising of hands. Have you ever experienced it? Okay, very good. Few people think they have. For the one that thinks that they don't, have you ever used Polaroid glasses? And then that use polarimetry. Or if you go to a 3D cinema, the modern one, where you can put these new fancy glasses, that use polarimetry too. But this is light, it's no radar polarimetry. But polarimetry is something that you can really make use, and it can be really, you can get a lot out of it if you know how to use it. And the basic idea is that when you change your polarization, you also change what you are looking at the ground or what you are letting you through. In the case of the glasses, what you are letting through, but in case of radar, is what you are looking on the ground. So by tuning the polarization of the field, by what you receive of the polarization of the field, you can really increase your discrimination capabilities. And the main tools that we use there is the scattering matrix, where you acquire this polarity information in 4 different channels. Sorry, got all entangled. So you acquire this polarimetric information in 4 different channels, and you can also represent this as a scattering vector here. So you see, if you in the Carlos, this is explained much better than here with a single slide. If you have a speckle, that you do for most of the targets that are down on Earth, then you need to use a covariance matrix. So you have this 3 by 3 in case you have quad polarimetric data, and you get information by doing these averages of the second order statistics of the scattering vector here. And one thing that you will see a lot later is this fancy with weird things here, the weird formula here. This is a quadratic form. So remember, this was the covariance matrix, so the data, polarimetric data, and this omega is a projection vector, or you can call it a scattering mechanisms. And when you frame them in this way, what you're doing, you are selecting the power coming from a specific target. So say you are interested in a target in surfaces, you select surfaces here, you put in these things, and what it comes out is the power that is being scattered backscattered by the surface. It helps you select what you want to look inside the scene, which is a quite useful thing, so you can imagine. You can tune this thing to what you are interested in to see. Now, the disclaimer that I was talking about. And this is important to frame these things that I'm gonna say soon. So I'm only reviewing recent trend, 2-3 years. And so things that have been proposed before this time frame or published well before this time frame won't be inside this presentation. It does not mean that that stuff was not good. It does not mean that the last 3 years are better, more worthy study, or more interesting than what was before. In fact, what was proposed before these 2-3 years is probably the gold of it. Is the most brilliant idea. Maybe they were proposed much earlier than the last 2 years. So I don't want to look like I'm looking down at this research, and I recognize the importance of all these many people. I have a long list here, but the list could be 3-4 pages that have contributed to what we have seen so far. But here I just want to talk about the latest thing, and I have to be selective, and you won't see the big achievements of 4 years ago, for instance, or 5 years ago. My apologies for that, but I only have 1 hour. I could have 45 minutes actually. I couldn't put everything. Another things, a big things that we're missing here is machine learning. We're not talking about machine learning, not because there is no development in the last 2-3 years. Most of the paper now are on machine learning. But the thing is that development at the moment is that using some methodology, machine learning methodology, developed for something else and adapt for polarimetric data. It's not really about polarimetry, about the physics, the geometry, the understanding of polarimetry. It's more about using these tools. So if we're talking about this, which is very interesting, but it's also be a branching off. It won't be anymore about polarimetry, it will be about some development in machine learning that people apply to polarimetry. That's why they're missing. Not because they're not good, there's no good stuff, but because we'll be branching off for what I want to tell you now. And application also not really talking about application, more about methodology, frameworks, so the new visions for the future, say the new way to process data for the future. If you are interested in application, there is an excellent book that you can read, and also falls into this 2-3 years time gap that I was talking about. This book, there's a series of applications in different domains, and you will find a lot of really late way of processing the data. You will, it's a very good overview of the community where we are at the moment, what is we are keeping in, and what all the applications that we can cover at the moment. I won't cover applications, but if you are interested in that, get this book. It's open source, it's open access, so you can just download today. Let's now start with the new trends. The first one I would like to talk about is this one, breaking free from convex polarimetry, which sounds like nothing, right? That doesn't mean anything. But soon you will discover what I mean with this. And yes, I'm working on this. I'm not the only person working on this, but I will present the way that I'm approaching it. And if you are interested in knowing more, these are two citations you can have a look at. So, polarimetric data. You imagine when you acquire this data, you have a three-dimensional vector. So you have 3 dimensions here. If you want to plot this thing, if you want to take a covariance matrix and then start plotting the quadratic form, so in other words, say you want to know how much power is scattered by which target inside the system, then what you will get is that the shape drawn is an ellipsoid. So when you take a covariance matrix, you try all the possible omegas that you saw in the previous slide, and you plot on this in this dimensional space, then you get the shape is an ellipsoid. So it has 3 axes, a major axis, and a middle and a minimum one. And this is what you get. There is no matter what type of data, what that you get, when you plot a covariance matrix, this is what you get out. But so to remember a little bit better, you can think about this graph, what I do with my students, because that are a bit more common. So it's like a spaceship, this thing, right? It's this 3-dimensional entity. The problem is that in reality, what you have is that you have inside your averaging window, so you have a 9 by 9 averaging window, you have 81 pixels there. Each of these pixels is a vector, 3-dimensional vector. This vector is going in some direction, right? And each one represents a pixel. Each pixel is a vector. So when you really plot these things, more than a spaceship, you will look more like a porcupine. So there are many pointy things. There is some preferential direction. So the most of the vector maybe want to go in that direction, but you have also something there, something goes there, something goes there. You have all this vector that comes out from the middle of the thing there. Now, if you average with a covariance matrix, then these things became an ellipsoid. But if you do look at these things, this does not have an ellipsoid shape in it. If you have a different smoothing function to put this together, what you will get is not really an ellipsoid, but it's more like, say, a potato. So some bumps. So there was some direction, it goes a bit more, then there is a bit less, then go more. It's not smooth. It's not like a convex shape, like an ellipsoid. So this is not convex because say, you cannot go from there to there without getting out of the shape, these kind of things. But this type of formalisms is very complicated. When you have a problem which is not convex, then you really struggle solving an optimization. It's not easy to do. So anyway, we are forcing this thing to be an ellipsoid, which but is not. So what is the problem of doing that? The problem is that the ellipsoid has 3 orthogonal targets, 3 orthogonal components. If you start with something which is not orthogonal to start with, let's say you have, this is one vector, this is your vector representing the ground, this is the vector representing whatever, the branches or some whatever, the trunks, whatever, and these are not orthogonal. When you do this transformation, when you do the average in a covariance matrix, they became like that, because it's forced. They are forced to be orthogonal when they are not orthogonal to start with. And this is not good, right? You are missing something there. Makes things simple, and it's cool, but it's really it's not really great. And there are situations, I think where it was a slide before, there are situations where this is not a problem, but there are situations where this became a problem. If you have seen the tutorial from Carlos 2 days ago, he was saying when you have fully developed speckle, it works very well. When you have one single dominant target, fantastic, it works very well. And In this case, it's the same. If you have fully developed and you have that inside the pixel, there is the same amount of target inside your averaging, so your averaging is the same representation of your pixel, then it's most likely you do have this fully developed as well, because there's a lot, and the best shape they can have is an ellipsoid. But when this is not the case, and you have patches, then it's not good, because you have a single target there. And you are still averaging with the rest, and you are forcing it to be something different, because you average with all the rest. So we come back again that when you are in this intermediate situation of not dominant and not fully developed, you. And so what is the thing that I think could be nice to explore, or the people are trying to explore, is using tensor fields. So dealing with these vectors as separate vectors, not as a covariance matrix, not putting all inside the same bucket and working with them, but dealing with separate vectors. The problem here is, of course, speckle. You cannot take a vector and read what is inside there, because the speckle will move it, saying this is original, this is what it should be. Because of speckle, that is created some statistical variation to all the 3 dimensions of these things. This will, you go reading it and you think it goes up, but in actual fact, but if you take all the vectors and go in target average, you end up with the right direction. So that's why we have, because the speckle makes your vector wobble, but when you average all together, then you come up with the right answer. So you need to average. Work single vector, it doesn't average discriminately, but you do some average at some point. Let's continue. The way you do it, things, is that you have to remove the effect of the phase that is related to the distance. You know, the phase of the is a component related to distance, and a component related to the target, the polarimetric. The component related to the distance, you just say remove the phase of one of the components of this vector. So you, what is called absolute phase, you can call it, and you look at phase differences. As long as you look at phase differences, you're doing a good job, you can continue. And then, well, there is the algorithm here, how you, it's like a chemical sort of field, and bunch vector together, and then once it's found a cluster of vectors, we average them together. Then still use of the average, so these things are averaged together, but you don't average vector coming from different clusters, only cluster first and inside the cluster. And this is done inside a search window, can be by length, whatever you want to use. And you have to select a number of targets. Just the clustering is more a clustering problem than else. These are the math, but it's all simple things. It's simple algebra, and just these things together. 5 minutes. So it's 45 minutes, the presentation. Okay. So yeah, this I do some Monte Carlo simulation to show that these things is true, is actually working. You can see that by doing these things, you can even discriminate between 3 different, so we have 4 targets inside the same resolution cell. You can still discriminate. If you apply the normal, say cyclopair, then so the normal way of covariance matrix, you will make big mistakes. You're not gonna succeed in that. Yeah, this is some example, and just why this is worth, because then you can really and components of targets, like in this case is iceberg. So iceberg is one of these things that are not fully developed, but also no coherent targets. You use this middle domain, and you can pick up different components. You can work on the structure of now, second thing, synthesizing information. There is a trend, well, I'll tell you this later with more details, but a new trend in synthesizing the try to find out the best way to use all this rich data. So polarimetric data, you see these 9 independent elements after you average. It's a lot of numbers, but what you try to do is to get from this 9, get just one, which tells you a lot. For me, it's like getting juice out of some fruit. So you try the most of it, so the flavor, most of the flavor will come from juice, but also you're losing the texture, maybe you're losing other things that will be inside the full fruit. So once you synthesize, inevitably you lose something, but you also try the main of it, the main juice of it, and by synthesizing, these things can be better fed to some, say, machine learning, or generally to understand what is going on, because you make everything inside a single component, so you make it easy to interpret. And I have to say this, how the most working on this transaction in India with the Bhavik, and then say we also will see Shubhadeep. It's very, you are a pro polarimetric. When it, I think you should be proud of unity about being fortunate with it. So the first one is from Avik Bhattacharya, IIT Bombay, and the main idea here is to use starting from the scattering matrix and then extract some out of it. I have way no time to talk about it. If you look at different type of targets, they will have different signatures inside the parameter. So the parameter is able to distinguish among targets. The way that I see it, in a nutshell, trying to see the amount of related to isotropic targets. Isotropic targets are like surfaces or spheres. They're very peculiar targets. And what it does is isolate the power from and one that comes from the rest, and use this as a discrimination way, like a discrimination criteria to separate all these. Unfortunately, we have the person in. If you want to know more. Why this is worth? Because this helps us discriminating steps, producing maps. Tell us that this is a surface, tell us that this is an urban area. So we get a single image for and this one is quite quirky, so I'm not sure if I have time to explain it fully. But what it is the capability of data to explore target in different bases. You saw in the tutorial of Carlos that you have an infinite of observers. You just took your action and you look at different targets, at different things. What this check for the consistency, for the coherence, so the stability of targets into different bases. You have the linear base, circular base, and this is the magical things doing through this correlation coherence here. The magical things of this is that if you have a target which has properties coherent in both the bases, then you will have a high coherence. If your target has properties which is not coherent in the two, then you have a value there. And it is all based on some very old stuff in the 70s called the Eunen fork of polarization. So there is a lot of background on that, but the end is a very single complex number which tells you all this information, synthesize what is inside the polarization fork. And to work with partial targets, you need to do this trick here. I don't have time to explain, but it's not very complicated to ask if you are interested, but you calculated the trace coherence. This actually. And again, I'll be quick, but as for before, why this is important? Timed information in polarimetric data not inside intensity, but is inside sort of the coherence of things. And if you intensity, able to see that these are aquaculture platforms. If you apply this methodology, they pop out and you can see them. It's able to this information, which is very important, just about density. So now, new generalization theories. This one is something that I proposed recently, but they're not the only one working on this. There are Alberto Alonso in UPC also working on this thing, but it's to try to find some model to represent changes in time. And the things that at the moment work time series as just observable. We don't really do much than say plotting a trend, but there is more than that inside the T. So there is a physical target which is changing in time, and we don't care about that mostly. We just plot some observable, and we see how the observable goes, and maybe interpret observable point by point. But we don't interpret the change, so we don't model changes. I think we should start doing it, because there is physics there, and can be exploited to understand what is going on. And normally, the one that I propose, two type of changes. You can have a change where you add stuff, like you add in an ingredient in your recipe. You can have a transformation change where you have something and this change, say rotate or get modified. In the cooking realm will be like heating up butter became melted. So you change it, this, but it's actually the same thing. While here you're adding something. And then a mix of where you add stuff, but you cook. So these are, I would say, the three most easy interpretation of changes. I also please ask the community to come, do you have mind, brighter than you are getting older. So please come with more ideas. So now we can model this change. This is the simplest that I could come up with, but maybe you can come with something cleverer. And so yeah, to explain a little bit. And this can be done also with optimization of quadratic forms, we were saying before. And here I'm using the covariance matrix, because we have nothing better to do. But if somebody in the future will come with something better than this covariance matrix with tensor field, maybe there will be a boost for the community to try to do that. So this is the transformation change, and just going quickly. Well, the slides I can give the slides as well. I can put this. We can put the slides inside the ISA folder. So remember the one for the practical. So I can put them there. So why this matter? Because with this classifying the change, you know that here over the sea, you have this blue color. It tells you that there is some extra surface scattering, some extra waves. It was windier, one of the two. Here you have some green. You know that there is some vegetation that is coming up. Here you have red. This is a caravan park. So some caravan was parked the first day and then moved, and some other was parked another day. And you can see where the things moved in between the two dates. So by looking at sort of the color of this image, which is the polarimetric information of this model, you can tell what is going on. You can see something changed. You can also tell what is going on. And if you go, but you have to use the right model. If you use the wrong model, so like you try to apply the power ratio to interpret the scattering mechanisms, then the color that comes out are off. You cannot use that. So it's important to use models. And this is another things from, very, very quick on this one, from Nikita Barsagin from DLR. This is trying to generalize the way we process SAR data, really in general, anything. And to me, it looks like, I don't want to downsize what Nikita did, but to me, playing with Lego, so using Lego, say, because you have this, and you pick an image, then this block together and became a covariance, and this block together became them. Up these blocks of blocks, create your structure, very complex structure. And the cool things of thing, so as I was saying before, so you have different dimensions here, and you can blocks. And the cool thing of this process is that the rules of engagement, the operation of these things are all the same, all defined. It's all this playing. So you can apply the same transformations. All this get information for all of it. So it's a way to generalize the way we process. It's not anymore a patchwork, but it's all built. And well, I need to be very fast, but there is some optimization to find out how to get this block built, the construction and reconstruction. And this is some example using some data. I think you saw also that from Irina Heinzek talk. But you can represent this in a change. Also, Irina showed you have changes. You can model the changes in time using this type of formalisms. And these are related, so if done, they are related to characteristics of the targets. And you can also attach a model, and then your transformation is model-based. That other fields, like ship detection, where we are trying to do generalizations. And in this one from Utah, and what we were trying to do is to find a way to unify all these detector that has been developed. And this one has been developed in the past, very famous names. You may know if you do ship detection. And they all, with very different equation, but they all end up in the same form. This is where C is your observable. Try to generalize, make all the things including theory. Yeah. So I think I need to wise word because you can detect ships in a better way. Like try to detect ships in this messy image, but with that you can. So now to the conclusions, and sorry if late. So I think at the moment we are at the end of a huge wave of development in polarimetric SAR. This was given by when we turn to the covariance matrix, so the scattering vector, and all the things related to diagonalization, decomposition, and optimization of the scattering of this covariance matrix. That was a big wave, but now that is probably fading down, and we are now ready to start a new waves. So looking at this problem in a different way, try to do generalizations, try to find better framework that can exploit this tensor field in a cleverer way. And I think this will be possible because the highest availability of operational data, so soon we will have biomass, which every single image is quadpole, and a better understanding of benefit and problems of, let's say, new polarimetric mode like compact. More, say, 10 years old, so it doesn't fit in these 2-3 years. But I think we still need to understand it a bit better to see what can we do and what we cannot do. And the new trend also could be in this better way of information. And we want to use them. And yeah, machine learning also will play a big role. And hopefully we also start seeing machine learning technology that are more physically based, so they don't lose. They start to include that. And this is the end of my talk, and hope for the future. future is bright for polarimetric data. So please come and join us, join the family.
Thank you, Armando. So we don't have time now for maybe questions, but Armando will be here today and tomorrow. So please discuss with him if you have questions or you want to discuss something. Thank you, Armando, for that wonderful talk.
Dr. Srinivasa heads the Web Science Lab and is the Dean of R&D at IIIT Bangalore, India. Srinath sir holds PhD from Berlin Brandenburg Graduate School for Distributed Information Systems, Germany, and MS from IIT Madras and BE in Computer Science and Engineering from the National Institute of Engineering, Mysore. He works in the area of web science that models the impact of the web on humanity. Technology for educational research and social empowerment has been a primary motivation driving his research.
Good morning. Thanks for the kind introduction. So this is more of a sponsored talk, and I really don't work in the area of geosciences or remote sensing. So this is from the Mphasis Center of Cognitive Computing. And we were seeing what project kind of comes closest to this community. Right? So then we thought, well, let us talk about our Karnataka data lake project, which probably might be of interest to the community here. So this is the project we did with in cooperation with the state government, that is the government of Karnataka, Department of Planning, and the SDG Coordination Center, which is from the UNDP, which is also having an office in the government of Karnataka. So this project was carried out a little more than about 18 months or so, where we kind of tried to understand, how different factors affect indicators that that manage our sustainable development goals. Right? And so let's start with a quick introduction to sustainable development goals. I'm sure a lot of people here are aware of the UN SDGs. So these are 17 sustainable development goals promulgated by the United Nations after the Millennium Development Goals that were pushed between 2000 and 2015. So this was an agenda for 2030 that we need to kind of reach about. There are about 169 targets, so there which member countries are expected to reach by 2030. Right? And so what this has led to is that several member countries, including India, of course, have embarked on a program of SDG localization. That is, how do we localize these targets or indicators to this context? So what works in, let's say, Germany may not work in Karnataka or somewhere else, right? And this is so I'll just go to this. Niti Aayog, which is the equivalent of the Planning Commission from the central government, is very keen on pushing SDG localization across the country, and they have also release periodic reports in this effect. So this is a problem that we are addressing, SDG localization, and we are addressing it using a data science kind of perspective. That is, the planning department basically said that we can provide you all kinds of data you want, but tell us what is it that we need to do to improve the indicators, that we are. So on several indicators, we are actually, the state of Karnataka, that is actually in a concerning state. For example, something like infant mortality. So I don't know the exact numbers. I think it's something like 63 to 10,000 births or something like that. So it's very high compared to the national average or the world average. And so what is it that we should do? So we can give you all kinds of data sets that, and you can also scrape data sets from the web, from other reports, and so this is kind of the big data kind of problem that we were looking at. So broadly the problem was very clear. Tell us what we need to do, but of course the devil lies in the details. And so this is where we try to kind of approach this problem. Okay. The main issue we found is if we have to approach SDG localization, right, we need to have some framework to talk about sustainability, right? We need to say, what is sustainability really? In fact, that's one of the questions we debated a lot in our lab. What is meant by sustainability, right? And so if you see that, if you understand sustainability from first principles, something that sustains, we see that we can't model this as a goal achievement problem, right? In fact, all the sustainable development goals and targets, for example, SDG 1, right? So this is one of the target over there. It says by 2030, eradicate extreme poverty from the earth, of course, measured as people living on less than $1.25 a day. Okay, so this is the target that is given. Okay, it's a very good target, and let's say we achieve it. Okay, and we are successful in achieving, but that doesn't remove the fact that this achievement may not be sustainable. Right? Today we may achieve it, tomorrow it may go back. Right? And the sustainability problem still remains. Right? And even after we achieve the targets. Right? And in fact, for those of us who are aware of Amartya Sen's approach called capability approach. Okay. Which is defined as capability is defined as the well-being of people should be understood in terms of people's capabilities and their functionings, right? And so if you look at this definition, all of the SDG targets are actually capability targets, right? They talk about building capabilities across, but it doesn't talk about building sustainability. It doesn't say, okay, this if we build this capability, it's going to sustain, right? And so the sustainability problem still remains, right? And so this is where we found the biggest roadblock. How is it that we are going to localize if we do not even understand sustainability, if we do not even have a framework for reasoning about sustainability, okay? So currently, if we look at the literature, sustainability is defined in terms of time. Okay, this is one of the very famous definition of sustainability. The Brundtland Commission, for example, says sustainable development is development that meets the needs of present generation without compromising the ability of future generations to meet their own needs. That's one thing. And this, for example, is a well-known graph by Constanza and Patton about sustainability, where they say that every system, right, whether we talk about a cell or an organism or a population or a country, economic system, planet, okay, it has some kind of a expected lifespan. So a cell lives for this amount of time, organism lives for this amount of time, and so on, right? And so if that system dies before this, it is unsustainable. And if the system lives beyond this, it is kind of brittle. Okay, it's too sustainable in some sense, or it's brittle, right? So anything that lives up to its expected is what is sustainable. So according to the definition. Okay. But we see that this definition doesn't really work, right? Say for example, if we say something we did is sustainable, and we are talking about an economic system, we probably will have to wait for 200, 300 years to verify whether that's correct or not, right? And so a time-based definition of sustainability doesn't really work, right? So we can't actually wait that long, right? And so we really had to kind of go back to the drawing board and try to revisit what sustainability really means. So this is what I'm going to present is the work of our PhD student Pooja, who is here. She has done a lot of work in building these core concepts here. So once we go back and talk about sustainability, right? Here are some of the things that we kind of realized about sustainability. Okay, one is, of course, like I said, this is not a goal. Okay, but it's a state maintenance problem. It's not a goal achievement problem, right? So we can achieve a goal, end poverty, but we need to maintain that state. Okay, that's when it becomes sustainable, right? And so we have to formulate it as a state maintenance problem rather than a goal achievement. And so that's the first thing. And second thing is sustainability is not a binary predicate. Right? It's not like something is sustainable or non-sustainable, right? And some states could be more sustainable, some states could be less sustainable, right? So there's a degree, right? So we can't talk in binary logic here, right? And third, of course, like I said, if we take a time-based definition, we can only say in retrospect whether something was sustainable. Otherwise, it's just a prediction, it's just an assertion that this may be sustainable, right? And And of course, and next is context sensitivity, right? The thing is, sustainability is not a property of a being in itself or a system in itself. It is also a property of the context in which it lives, right? And so if we change the context, what was very sustainable once may become very unsustainable. Best example is of the dinosaurs, right? So they were, of course, very sustainable. They were one of the biggest creatures on the planet, but the context changed, and then they're no longer sustainable. And, or even in businesses, you know, Nokia or Nortel networks, they were once reigning the mobile landscape, but then the context changed, the technology context changed, and then they were no longer sustainable, right? And so sustainability is not a function of a system in itself, but the system and its context. So we kind of get of course, this is another important thing. There's a conflict of sustainability between individual and the collective, right? So the best example for this is, suppose we work hard and we improve individual health so that longevity is improved. So everybody lives for 80, 100, 120 years, right? And which is great for individual sustainability, okay? But it also means that there's a greater demand for resources, right? So what happens to the collective sustainability, right? So there's always this conflict or between, you know, should we optimize for the individual or should we optimize for the collective? You know, so that's one more. And of course, sustainability is not a virtue by itself. In fact, some of the like we said, poverty is very easy to sustain than wealth, right? And poverty is very stable. We can sustain it very easily, right? So it's not a virtue by itself. We have to improve capability in addition to sustainability, right? So that's one of the things. So these are the axioms we kind of developed as part of this work, and using this, we developed a logic, okay, what we call a logic of being. Okay, so I'll quickly explain what this logic is. I'm aware of the time constraint, so I'll just want to kind of explain the core idea of what this logic of being is. This, okay? So yeah, so basically what we said is the unit of consideration is what we call a system of being, or simply a being. Okay, we call it A. The being can be in different states of being. Okay, so and each state of being has a particular sustainability. Okay, so how do we define sustainability now? So we define sustainability now as resilience in the face of perturbations, right? So what is the magnitude of perturbation that can dislodge the being from this state, right? And so now we are defining sustainability not in terms of time, but in terms of resilience and perturbation, right? And of course, we normalize perturbations between 0 to 1. So that you know, the bigger the perturbation that's required, the more sustainable the state is in, right? And then we say, of course, every given state also has a capability, and we define capability as a vector. So it could be all our targets and the vectors normalized between 0 to 1. So that's our capability vector. And the environment of a being is termed V of A. So the being in interaction with the environment of its being, okay, we say that results in a non-cooperative game, and every finite game we know has an equilibrium. So this comes from the Nash equilibrium principle, that every interaction, a finite interaction between two agents has a Nash equilibrium, right? And so this is what we term as E of the equilibrium point, right? And so now any given system in an environment, okay, ends up in its equilibrium state, okay, mutually best response state, and that equilibrium state has its own sustainability and capability, right? And so our problem now is to curate the environment so that we maximize this, that is the sustainability and capability of the equilibrium state, right? So that is the logic very quickly that we developed. Okay, so let me go to a case study now. So what we did is, so this is one of the case studies where we looked at a policy intervention about crop yields. And the policy intervention, I think here got to do with the amount of NPK, the nitrogen, phosphorus, potassium fertilizer that's dispersed, right? And so what is the environment? So what is the being here? Being here is what is called as an agroclimatic zone. So the state is divided into different, I think about 10 agroclimatic zones. And the neighboring agroclimatic zones are the environment for a given, okay. And the equilibrium is modeled as a stress reduction problem, right? So stress is basically defined as the difference in capability. So so basically as system, so this the typical annealing principle for those of you who are aware of machine learning, the typical annealing principle. So the equilibrium comes to low stress model, right? And so this is the idea of the stress reduction model. And yeah, so we also built some models, built quite a few Bayesian models where we identified different factors that correlate with crop yields, and then built a factorized Bayesian model. Later on, this proved to be quite an overkill, so we just built a multivariate regression models for this. So the basic idea is if you change any of these factors, these things will change, okay? But that will result in some perturbation, and the system settles down to some place, right? And so here is a quick idea of where it settles down. So if we increase NPK distribution by 10%, okay, we see that in most cases, it makes hardly any difference for rice yield, right? In fact, in some cases, it comes down, the yield comes down. Some places it kind of goes up a bit. And wheat is really, perturbed all over the place, right? And so it's very unstable in terms of. So in fact, what we said is this is not a good policy intervention, because it doesn't actually yield. Yeah. Okay. So so basically what we finally did is we have this scatter plot, which is a impact versus stability plot, right? And so for any policy intervention, we have this impact score in the y-axis, the stability score in the x-axis, and this is the median impact and this is the median stability. So all the districts that come up here are the most impactful and most stable in terms of this intervention, right? And so that's how we kind of provide, and these are where we should concentrate. Okay, yeah. So that's about it. So I'll just quickly show some dashboards that we have done. So this is a predictive modeling dashboard where we say that suppose I think this is about MMR, the maternal mortality rate, and we increase some, we change some values. I think having to do with BMI index or something like that. That is improve the BMI reading of average BMI reading, and we see that the best, the green ones are the districts where we find the best impact and best stability, right? And the red ones are, and we can drill down like this. And we can also do prescriptive modeling. That is, if we want the target to be here, how should I change all the factors that are correlating with it, right? And so this is the prescriptive modeling dashboard. And we can also do budget allocation based on this, right? And so this is the budget allocation dashboard, right? And yeah, being shown that there's 1 minute remaining, so I'm pretty much done with. So this is the kind of work that we did. Yeah, this is basically the overall pipeline and the architecture of the data lake and the data flow pipeline, and yeah, kind of that's about it. So I think, and we plan to expand it to more targets and more indicators and so on. So with that, I would like to stop. I'd be happy to answer any questions. Yeah, so this is our team. This is very long.
Thank you so much, Professor Srinath. I'd now like to invite Professor Y.S. Rao of IIT Bombay to present a memento to Professor Srinath.
Thanks.
Thank you. We'll take questions at the end of the session since we are running late. Now we will start the short talk by Professor Uttam Kumar, IIIT Bangalore.
Dr. Uttam Kumar is an assistant professor at IIIT Bangalore. He is a senior member IEEE and senior member ACM, and is the former Mphasis Foundation Career Development Chair Professor. Dr. Uttam holds a bachelor's degree in computer science from Visvesvara Technological University, Belgaum, diploma in advanced computing from CDAC Pune, master's degree in geoinformation science from University of Twente, the Netherlands, and PhD in algorithms for geospatial data analysis from Indian Institute of Science, Bangalore. He earned professional certifications in data science and machine learning from Massachusetts Institute of Technology, in big data from Stanford University, in spatial computing from University of Minnesota, and in geospatial intelligence and revolution from Pennsylvania State University, USA.
Good morning, all of you. So I am here to present a small talk about our very popular center MINRO, and to highlight some of the initiatives that we are doing in the geospatial domain as part of the MINRO center. So MINRO basically is a center which stands for Machine Intelligence and Robotics, and it was established by the government of Karnataka on recommendation of the Karnataka Knowledge Commission, and it is considered to be a best-in-class center of excellence for research in machine learning and robotics, and more essentially in the area of applied data science, applied machine learning in the Indian context. So the MINRO Center at IIIT Bangalore promotes multidisciplinary research, and also promotes development of open source platform for various domain for technology transfer. So here we have the broad charter is to carry out research in the area of machine intelligence and robotics, and there are few research objectives that each of us are trying to focus on. So basically the idea of the center is to see and to promote fundamental research in machine learning and robotics, encourage a multidisciplinary approach to research, and it promotes collaboration between institutions, between startups and academics, and also helps in following policies and framing policies and framework for responsible AI. And finally, the overall goal is to disseminate the information to the public. So these are some broader statistics the center of the ongoing projects. These may not be updated values, but on an average, we have currently large number of projects going on and large number of publications coming out of the center. Okay, I'm going to quickly highlight few of the main research areas in MINRO, and in what way they are impacting the society. The first among them is faculties working on assistive and technology for Divyang. So two faculties have looked into chart image digitizer for visually challenged people, and also refreshable braille reader developed at the MINRO center. So there are robotic arms that have been designed for surgical assistant, and there are research currently going on in multimodal language translation. So this is basically research being carried out by Professor Dinesh Babu, and he has come up with a cognitive interview assistant system that has been practically used in administrative services both in the state and at the center level. And there are other related to AI where speech to text translation for data, etc. have been attempted. So coming to the robotics application, so there are currently work going on in the area of warehouse robotics, where the idea is to minimize the workflow, and the idea is to complete work practice without much disrupting the warehouse design. And then there are works currently in the area of mobile robots and drones and collaborative robotics, where the aim is to see that we reduce the physical effort, and we also minimize the training for the new people in the manufacturing sector. Coming to the impact on society, so we have a program on digital society, and MINRO is an active participant there. So people affiliated to MINRO from digital society program have been trying to impact society in a larger ways. They are trying to look to equity in public transport, trying to humanize automation. So this is basically a kind of a framework for evaluating how automation and human human beings can complement each other. So there are a few tasks, for example, trying to develop a framework that can improve maybe inter-ward bus connectivity, and trying to see or develop automated methods that can annotate labels for AI applications, etc. So these have been tested in some areas like retail banking and data labeler. The next research currently going on is in the area of urban mobility. So here Professor Srinath, who just gave a talk, has done a lot of research on adaptive traffic lights, and these have been essentially implemented in parts of electronic city. So they have worked on virtual traffic constructor, traffic simulation for road network management, etc. And you can see a few results out of that research here. Web observatory and social media is again another task which Professor Srinath has carried out, and there they are trying to look into AI-based social media intelligence. So the idea is to detect concocted campaigns, and they have focused on online social cognition, trying to understand the drivers and also to detect fake news. In terms of medical science, few faculties have carried out a lot of in-depth research, including trying to look at the fundamental for segmentation, which basically in some sense help in diagnosing diabetic retinopathy. And there are few works related to emotion recognition with the EEG signal, which is also currently going on. So the center has in a great way impacted the startup ecosystem, and there have been collaborations, multidisciplinary research, startup mentoring by the faculty, and a lot of open source platforms, open source softwares have been developed as part of the MINRO initiative. Now I will move on to the next part of the presentation, and before that there is a MINRO Gyan Sarani YouTube channel, which basically provides knowledge on different areas, different themes related to AI and its applied domain. So let us now shift the gears and move to the next topic on looking at some of the geospatial initiatives that are being taken at the MINRO Center at IIIT Bangalore. So one of the very important areas where we have currently started working in is agriculture, and this slide basically highlights few research areas that our group currently focuses on, looking at global vegetation cover, tree detection, crop classification from UAV images, looking at urban mobility and human detection, object detection, and so on. This is a glimpse of our lab and some of the activities that we do, including some meetings. So you can see Jaya and me standing here, and in our recent meeting with the ISRO. So the current focus of the ISRO project, and thanks to NRSP who have funded us the project on digital agriculture, and this is a nice initiative to solve some of the problems. And what motivated us to take up the problem is as follows. So look at the status of Indian agriculture as of now. See that Indian agriculture contributes roughly 17% of GDP, consumes 22% of electricity, deploys 50% of manpower, and consumes a massive 80% of water resources in India. So the 10th, as per the 10th agriculture census, which was conducted in and around 2015 and 16, it revealed that small farmers who have less than 2 hectares of land, they constitute mostly around 80% of all the farmers in the country. So what more was revealed is that these farmers only own 47% of the crop area. So we see that there is a huge demand to do more research in applied science, for example, agriculture, and moreover, changing rain pattern, farm practices, and so on, they have greatly impacted the agriculture sector, not only in our country, but across the globe. So this motivated us to take up, to draw certain challenges that people have observed, and we also came up with few discussions that include crop health monitoring, crop nutrient assessment, detection of crop disease, valuation of damages caused from disasters like flood, and then timely estimation of crop yield. So we saw that because of these problems, both the productivity in terms of quality and quantity are impacted. and more often than not, the disease remains unidentified. So there was a need to develop some kind of a software or AI-based software that could help in detecting these disease early for a fast and reliable method, which is required for the benefit of the farmers. So let us now see what are the focus areas of our new center or of digital agriculture. We are looking into crop health, soil health, nutrient efficiency, early stage disease detection in crops, and yield estimation. And the overall idea, as also requested by NRSC, was to develop an app-based solution to solve all of these problems. There are other allied areas including automated mapping, automated classification, climate change, and urban informatics. So how does it impact the farmers? So farmers will be helped in a great way. They will get to know their crop health. They will be able to know early detection of any kind of disease in the crop. And finally, which is more important, is what they will be able to get an idea about the yield of the crops. So we went ahead and we have just initiated developing a mobile-based app to help or assist the farmers to solve some of these problems. And the app basically is being developed to manage, to empower farmers to record their farm, to record the type of variety of crops, to give to put details, to build up a database, and finally which can be used for basically yield production and also for disease detection. So here is a screenshot of that particular app called Kisan Dost, and we have roughly some very key features that we are planning to implement. Some of them have been implemented, including farm creation, crop management, data generation, and disease detection. And finally, the most important one is yield estimation. I can talk about this later after the talk. I can discuss on all of the parameters. So these are few screenshots of the welcome screen and the more elaborated view farms and the kind of details that can be uploaded. And these are some more details on crop data, growth parameters, yield parameters, and so on. So the app is currently in development stage, and the idea is to just take photographs from the fields from mobile cameras and use it to predict yield, and also to predict some of these water stress, look at the disease and nutrient deficiency, and so on. There are other challenges that we are also trying to handle at the same time, including trying to look at the different types of crop apart from what we have already started. Look at the scaling parameter, that is, we need to move from village to taluk to state to national level, because most of the machine learning model that we have worked on works for a smaller data but do not scale well at a larger scale, and trying to develop methods to annotate samples automatically, thereby reducing human effort. Here is an attempt to detect this using a semi-supervised method using convolutional neural network. And here the main contribution was that we have completely minimized the generation of training samples and annotations. And this is another work on plant disease detection. So here we have samples from the plant village, the plant sampling dataset, which are available in Kaggle. And then we have some work done on crop classification using UAV data. Basically, UAV sensor on multispectral data has been used using CNN. The Altum camera has been used with six spectral bands. And here is another work where we have tried to detect power lines which generally occur on top of the agriculture farms. So we have worked on with a method to detect these power lines. Here are some publications published in Neural Net. Recently, this was accepted in NeurIPS, and this was accepted in Scientific Report, and this was presented in IIIT, and this was in Chaos, Solitals, and Fractals. These are some more publications relevant to the current research. And with this, I would like to conclude, and thank you for your attention.
Thank you, Professor Uttam. Now I would like to invite Professor Chandrasekhar Ramanathan, Dean Academics, IIIT Bangalore, to present a memento. So we have a couple of minutes. We can take questions for all the three plenary speakers.
So, sir, you were explaining about that disease detection. So, and how you are training models based on the photographs you are taking from the farms? What is the basic approach?
Yeah. Initial experiments that we have carried out and that I have shown on the slide. So those were taken from the sample database that you may be aware, plant village dataset and plant seedling dataset. Both are available in Kaggle with ground truth. So they are perhaps taken in a controlled environment, but we have now collaboration going on with ICAR, who have a big database related to different types of diseases, different types of crops, and they have agreed to share the database along with the complete data. So we will not try to scale up the existing machine learning model on that big database. Obviously, it's not possible for us to collect the data and even identify the disease. So we needed some help who are expert in that area.
So can that, the algorithm what you have developed can use photographs through drone also?
Yes.
Okay.
Yes.
Because that would be more practical approach, because you can fly drone over the entire field and take photos and just detect diseases.
Yeah. That is the overall idea. Because we cannot have taking photographs from a mobile. So the ultimate idea is to use the drone data and detect the
So that is the ultimate aim.
Yes.
Okay. Okay.
Which type of sensor for photography you are using?
So we for the UAV data we are using an Altum camera that has 6 bands, 6 multispectral bands, including thermal band and 2 red edge band. So that perhaps has been found to be useful for detecting disease and detecting plant types. Apart from that, the app which I was trying to show, that for that we are trying to capture photographs through mobile, because that is ultimately to help the farmers. So they should be able to collect data on their own from the smartphones.
But that will vary, na? If you one take from mobile, then how you classify that?
So we are creating a framework where the software will automatically assist you to tilt the camera or to get away from the take the photograph from a more distance. So it will guide you to in the way to take appropriate photograph. Then only the photograph will be accepted and saved.
Basically, mobile cameras, some are sensitive to color, some are sensitive to the textures.
Yes.
So how you identify those things?
So
because a different camera are there.
We are currently correcting lots of images from different cameras, so that the model is finally trained to take any type of images. Perhaps they will definitely follow some guidelines such as distance from the object, the oblique angle, etc. And beyond that, we are making a rich database so that it can handle all types of variations in the camera. Yeah, we can discuss.
Yeah, so are there any more questions?
Sir, it's a nice presentation, sir. So regarding the last few slides, you were mentioning about the power lines.
Yes.
And its detection. In what way it will be affecting the yield or in your application?
So it is not going to affect the yield, but the thing is, if there is a problem in the power line, and suppose if the cable breaks, okay, then in case you need to find out where this problem has occurred, it's not manually to traverse along the power cable and see where is the damage. So if there is a UAV data, we can right away use this algorithm to check where is the problem, at what site, and immediately go and try to rectify the problem.
Okay, so these power lines also you are detecting using the AML techniques?
Use the AML techniques.
Okay, good. So which technique you are using, sir?
So we have UNet for that and a few segmentation techniques. So the training part is more difficult because there are only 6-7 cables in the whole image. So major part is non-cable and very small part is cable. So it's something like a one class problem. So it takes some time to develop the training data itself, but the results are quite satisfying.
Okay, thank you.
I can share the paper.
Yeah. Thank you, sir.
Good morning, sir. Actually, you have shown some images, right? Those are related to the fungus or virus infections. Are you working on the pest infection also? Identifying the pest infections?
So the overall plan is to work on those pest infection data also. Right now, we do not have that data, but we are in touch with NRSC and touch with ICAR. So they have agreed to share that data, upon which we will then try to develop the model, AI model.
Okay, thank you, sir.
Just a quick question for Dr. Srinath, if I could. It's very interesting to see your sort of perspective towards this measurement and towards the SDGs. I was just curious to know if the Karnataka data lake has some data available for independent researchers or open to the public in some way that we can also access and do some analysis on it.
Right. Thanks. So yeah, in fact, the pilot site is available. It's there in the slides, kdl.iiitb.ac.in. The actual site will be inside the planning department. So the pilot site has some data sets which are public. So there is a data lake interface where you can download the sites. Yeah. So there is a bigger roadmap, which most of it is a policy-driven roadmap. So the policymakers are doing that. So yeah, it's not publicly accessible.
Yeah.
Correct. Yeah. So primarily, we were not working on the traffic lights itself. We were actually looking at if we have to put adaptive traffic lights. So there are quite a few solutions for adaptive traffic lights, which will measure the amount of queue length, of the vehicles that are standing there, and then appropriately change the duration of. What we actually saw that is, if I have a grid and I make every traffic light adaptive, it will actually make things worse because each one will optimize for itself and it doesn't actually get. So our problem was through simulation to identify which are the points in electronic city where it is best to keep the adaptive traffic light. So the red points in that map that you saw were the points where we said that this is the most ideal point where you can.
Yeah, thank you. One question. So regarding the mixed mode of traffic conditions, basically, if it's very same type of vehicles, fine, but if we do have a mixed mode of traffic conditions, how you are trying to find out the solution for the mixed mode traffic?
Yeah, so like I said, we are not looking at the traffic light design itself. That's a very detailed question in itself that typically they are based on PCU measurements, passenger car units, but then you make each different kind of vehicle as some variant of PCUs, and I think that's how most of the adaptive traffic lights are designed. So we didn't actually get into that. We said, okay, whichever is the design, we just want to find out in a grid what are the optimal points where you can place them, which you can make adaptive.
I think the traffic lights that you talked about are now connected to Google Maps.
Right. Yeah. So they either estimate the queue length on Google Maps. Some of them have cameras, some of them look on Google Maps.
Thank you. Any questions? I have a question for Dr. Armando. So I have some interest in tensor fields. So I wanted to ask you the kind of tensor decompositions that you do for PolSAR. What is the dimensionality and the order?
At the moment, they're not going in that direction yet. Okay. This is what I think we should do. Okay. So at the moment we have, so these are three-dimensional complex. Mm-hmm. So each element of the covariance, the scattering vector is a complex number. Right. And yeah.
So so what does the decomposition give you eventually? I mean, what is the plan for the decomposition? If that's
so
futuristic.
So the way that we, so it's a way to avoid doing averages of an area indiscriminately. So the problem that we have speckle in SAR data. So speckle means that you cannot trust the results of a single vector, mm-hmm. because the direction of that vector matters, will be very much influenced by the speckle. Yeah. So you need to average vectors together in order to get something that is more stable. The problem is that how do you do this average? So it's sort of a filtering problematic. And the way that we are normally doing is by just taking a box and averaging everything together. So you will have say a 11 by 11 area. Each one is this three-dimensional vector, and you average all together with the second-order statistics to produce a covariance matrix. That is problem because you then put together too many things that are very different. Your assumption are not met anymore, and you make mistakes. As you see, you only can only get 3 orthogonal targets, while you don't have 3 orthogonal targets there. In the future, by not going through this indiscriminate average, you will be able to extract more target than 3 inside a single searching window, say. So this sounds a little bit magic, because you have 3 dimensions and you want to extract more than 3 not independent, 3 things out. But the thing why you succeed, because they're not independent anymore. They can be not independent. So the vision for the future is to be able to extract information without forcing the tensor field to be convex.
Yeah,
so not forcing the...
Yeah, so if it is not independent, then you have some scope for minimizing the rank and reducing the tensor itself, the size of the tensor then? Is that the idea?
No.
Okay.
Yes, is to don't go through that things together. So to don't go to the covariance magic. Once you go there, there is no, it's lost already.
Okay.
So you cannot, you have to do something before you go there.
Oh, okay.
Otherwise it won't work. So once you have the covariance matrix, everything is lost, say. So you have to do it before. And that's why it's problematic.
Right.
Because what do you do if you don't do a covariance matrix?
Right. Definitely. Thank you so much, Armando. Yeah, so if there are no further questions, Carlos. Is it for Armando? Yeah.
Thank you, Armando, for this super nice presentation about the filtering. Okay, I agree with you. We have to go beyond the filtering itself, but there is one point in the middle, as you said, that we get rid of a speckle through the boxcar. Okay, you filter spatially, but beyond abandoning the filtering, the new speckle filtering approaches are doing filtering with a variable equivalent number of looks on the image, which is, in my opinion, not really correct, because you have to treat then each pixel differently. So from your point of view, which should be the direction? I mean, not, as you said, the future of averaging, but which should be, for you, from your opinion, the way we should address the estimation of the covariance matrix, or at the end, the filtering, speckle filtering?
The covariance, we still can obtain a covariance matrix, but that covariance matrix can only be obtained if the assumptions are met. So that they have to be either a dominant target or a fully developed one. So this way here is approaching it by separating the dominant targets and then averaging, produce a covariance matrix only for that. In that way, you have something that in theory will be rank 1, in practice, no. So we will have what the people 40 years ago were calling the composition where you have the target and noise. And you could do for waves, because for waves, really, you have 1 and then noise, but you cannot do it here, because you can have situation where you have 3 dominant targets, and you cannot say 1 and noise. Because you have more dimensions. It doesn't work with the target polarimetry, it works with polarimetry, that thing. So the direction is to try to do a selection of pixels before applying the covariance matrix. Before going to the covariance matrix where your assumption will be met, or find that way to see if there is fully developed speckle from a polarimetric perspective, and not just from so if you have patches, you have a patch of surface, a patch of very dense forest, these are fully developed, but they are separated. Here you have no surface, here you have no forest, and if one is pointing there, and one is pointing in that direction, which is not that orthogonal, by averaging them together, you force them orthogonal. So you change the direction of the 2 vectors, and this is where you lose where there is the problem. So,
yeah, but this goes to the traditional
filtering.
No, to the idea that you have to be homogeneous, no?
Exactly, yeah, the assumption is broken, and that is the problem. The assumption, we force these assumptions, but assumptions are not there, and they make us making mistakes. We do make mistakes about that. And one problem with the normal filtering methodologies is that you need to have connectivity. So if they're not connected, then you have a problem. But we can talk later.
You talk later. Thank you very much.
I'm so sorry. Yeah, I think we'll take a break now. We'll do a 20-minute break and reassemble at 11:35 for the next session. Thank you so much for attending the plenary talks. We look forward to you being here for the next plenary session. Yeah, thank you so much. Yeah, see you.